Hi, welcome to the analysis, design, and simulation of a forward converter, part 6. Okay, in this video lecture, I'll be discussing the two-switch forward converter instead of the single switch. There's plenty of examples on how to implement a single switch forward converter. So I'll concentrate on the two-switch forward converter, and my main goal is to show how to implement it. Okay, and you'll see why I mean how to implement it. On the two-switch forward, if you refer to the schematic, you need one switch, and typically this is called the low switch, and the top, the high switch. Okay, and typically these are a little bit more difficult to implement simply because you have to put a voltage of approximately 12 volts to ensure that your Mosfet turns fully on. Okay, and typically you want that voltage from the source to the gate. Okay, and you want 12 from gate to source. Okay, and if you look at this node, when the switch is on, basically you have a short. That means that the source is going to have 28 volts. Okay, and if you have 28 volts, that means that the gate has to be 12 volts above the 28. In other words, you have a floating power supply. So basically your gate, if you were to take a measurement from the gate to ground, you would measure the 28 volts, which is at the source, plus your 12 volts. You would actually read 40 volts, okay, from the gate to ground. Okay, but from gate to source, you would only read 12 volts. So that's one of the problems in implementing. Okay, so since you have a floating node, this you need a special either driver to be able to drive this high side transistor. Okay, and one of the other problems is that you want to be sure that they both turn on at the same time, because it doesn't make any difference whether this turns on or the other one turns on. If they're not turned on at the same time, you do not energize the primary. Okay, so how do you do that? One of the simpler ways to do it would be to implement what is called a high side driver. Okay, now there's this is the IRS 2182. Okay, and basically you input your voltage here, or your gate drive, from the PWM, and it has a charge pump. Basically you have this diode which is connected to VCC, and basically you have a little charge pump that actually puts 12 volts or charges 12 volts on this capacitor. Okay, that capacitor is connected on the source of the top driver. Okay, and internally it switches the 12 volts into the gate. So basically this 12 volts is a floating driver. Okay, and energizes the top, and it also has a bottom driver that also puts 12 volts on the gate of the bottom transistor, or the bottom Mosfet. Okay. Now that's one of the ways of doing it, and sometimes these may or may not be expensive, but there's other companies that make high-low drivers, so you may want to investigate which are suitable for your needs. Okay. And basically, like I mentioned, that it uses a charge pump, as I explained, and this is a good way to drive or implement a two-switch forward. Okay. Now there's a second solution, and I'm going to concentrate on this one, okay, because I haven't seen too much documentation on how to implement a gate transformer with a DC restorer, okay, and I'm going to concentrate on that, okay. Okay. Now, a gate transformer is basically just the transformer, and typically you'll have a 1-to-1 ratio, or you can have a 1-to-2 ratio, okay. And in our case, we want to be sure that we have a 2 secondary, because we want to drive the low side with the bottom transformer and the high side with the high transformer, okay. And I would suggest, if you want some more information, go ahead and go on the internet, and you should be able to find this guide. It's a PDF file by Patrick Scoggin, which is entitled "A Guide to Designing Gate Drive Transformer." It gives you very good tips on how to select the frequency, the magnetic type, and it gives you the equations on how to actually design the turns ratio. Okay. So the gate drive transformer will look something like this. Okay. You'll have a primary on the gate drive, and you'll have a secondary for the low and a secondary for the high. Okay. And this would be, let's pretend that this is the PWM. Okay. And typically PWM will have anywhere from 1 to 5 ohms. So that would be represented by that. And typically you want to use a capacitor to couple this voltage into the transformer. Otherwise, if you do this, in other words, connect it straight in direct, you'll violate the volt-second rule. In other words, you'll have 5 volts when it's on, but then when it turns off, you don't get a chance to reset the voltage because it's clamped at 0. So if you put a capacitor, then it avoids you saturating the transformer. So that's a big thing to remember, that you need a cap in series with it. Typically, maybe a 1 microfarad or higher would probably be good enough. Okay. And on the secondary, you'll have these windings, and I'll go ahead and explain this in a little bit, but this is a DC restorer. Okay, which is this part, DC restorer. Okay, and what I want to do is I want to go ahead and simulate. That way you get a little bit more in depth. Now, what I did is I went ahead and did a Google search for a transformer, and I went to the Mouser, and there was this data sheet. Basically, this data sheet. Okay, it's from let's see, what company is it? Epcos. Okay, and the one that I would use would be this one. It would be a 264 microhenry, and it has a 1-to-1-to-1 turns ratio, meaning that the turns ratio on all three windings are the same. Okay, so once I have that information, and basically the information that I'm looking for in order to simulate is that which is the primary inductance. Actually, it's the inductance of all three of the windings. Okay, and then the other one that's of interest is that this is, they call it A stray, and it's 0.3 microhenry. In reality, this is really the leakage inductance. Very important. Okay, and once I have those two, I have the primary inductance and I have the leakage inductance. Okay, then I use these excuse me, to extract K. Okay, and I need K for my simulation. Okay, so you might want to ask, well, what is K? Well, K is the coupling coefficient of the transformer. In other words, it tells you how efficient your coupling from the primary to the secondary. So if you have a coupling of 1, that means that you have 100% of the flux of the primary going to the secondary. Okay. Now, in reality, you cannot achieve 100%. You can achieve close to it, and that's what these equations tell you. If you have a coupling coefficient of 0.99, that would say that 99% of the flux is coupled through. Okay, so with that, we'll go ahead and use this equation, which is the coupling coefficient, and it's the square root of 1 minus the leakage inductance divided by the primary inductance. So in this case, I have a 1 minus 0.3 divided by 264. And remember, these are units of microhenry, so they cancel out. Okay, so I get a coupling coefficient then of 0.9994, which is pretty efficient. Okay, so this means that this is a good high quality gate transformer, and I would use this to set my core spice element. Okay. Oh, and another thing that I like to warn you or make note is when you first do a simulation, you might get a little bit of ringing in your waveform, and I'll go ahead and show you how to damp for those. Okay, so let's go ahead, go with the simulator. Okay, and here's the spice. And let me go ahead and zoom this in a little bit. Excuse me. Okay, let me turn off the grids. Okay. Okay, so here I have L6, and I have assigned it a value of 264 micro, and I have the secondary, and I'm only simulating for right now, just for simulation purpose, a single output gate transformer. So the secondary will also be 264. Okay. Now we have this spice element, which is supposed to simulate the core. Okay, and you have to assign which inductors are to be coupled to each other. Okay, so in this case, when I double click, since my primary inductor is L6 and my secondary is L7, I put a L6 space L7 space, and then you put the coupling coefficient, the K that we just calculated. We set it here by putting a space and then typing the coupling coefficient value that you calculate. In this case, I calculated 0.99943. Okay, and I have my capacitor here. I'm using a 1 micro. Okay, and then I put a little resistor, and that would be to simulate the resistance of the PWM. And of course, this voltage source would simulate your output voltage. Okay, and let me go ahead and show you how I set this up. Okay, this is my pulse source. In the initial value, I set it to 0, and I want it to pulse to 12 volts, which is here. Pulse value would be 12 volts, and I do not put a delay time, so I leave that blank. And I want a rise time of approximately 10 nanoseconds, so that's defined here, and then the fall time 10 nanoseconds. Okay, now the next one is pulse width. Okay, and I do something a little bit different. It's a little bit more of a advanced SPICE directive. But what I like to do, instead of going back and forth and changing these numbers and opening the menu and typing in the pulse width and the period and so forth, I like to do a statement, which is curly brackets, duty cycle divided by frequency, close curly brackets. So basically, the duty cycle divided by the frequency will actually give you the pulse width. Okay. Now for the period, which is reciprocal of frequency, we do the same. To define the period, we define it in terms of the frequency. In this case, it's curly brackets, 1 divided by the frequency, close curly brackets. Okay. Now these duty and frequency are now are called parameters. Okay, so they've been assigned. I guess you can say that these are variables. Okay, and since these are variables or parameters, now I have to define them by typing in a text. And basically, you go to text and you type dot param space frequency equals 150,000. Okay, so which is what I did right there. Okay, so you type that, and in this case, duty cycle, since I want a duty cycle of 50%, I define duty cycle as 0.5. Okay, so now instead of opening the icon, that's one button, and then pressing this, and then defining this this column and this row and this row, to me it's much easier to come out here, modify this, and it modifies it automatically. Okay, and let me see. Okay, so now let's go out to the secondary. Okay, I want to go ahead and put a resistor here in the secondary, and that's to simulate the resistance that's in the winding. Let's go ahead and go back and see if there's a value for the resistance. Actually, if you look here, it actually has a value of 1.5. So let's go ahead and excuse me, I have a little bit of a sore throat. I'll define that as 1.5 ohms. Okay, that would be the series resistance. And excuse me. And let me go ahead and change the position of that just to show that it's in series. I'll do it like that. Okay. And then this capacitor will say that it's a 1 nanofarad, and that would be a typical value of a Mosfet, gate to source. Okay, can be anywhere from 1 to 5 typical values. Okay, and I think we're almost ready to simulate, and if we wish, we can add a resistor here in series as well, since it's specified in the data sheet. Okay, got the simulation. So now I'm going to do a transient. Okay, I'm gonna, this is your time step. I set it to 1 micro, and I'm going to shorten this up a little bit. I'm going to go to 250 microseconds. If I need to expand it, we will. And then the ceiling step is 20 nanoseconds. Okay. Now to display a waveform, you use the pound or hashtag autoplot, and the way to do that is you go to the text object and you put pound or the auto hash. You put auto plot and you can put a space V, and I'll put gate. Okay, and since it's a transient, I label transient, and I want that to appear in waveform 2, and I'll do the same thing here. It's a transient, and I'll want this to appear in plot 1. Okay, so right now I just want to plot the in gate. Okay, and I want to hide this or disable this, so I put a star, and what it does, it comments that. Okay, so then I'm ready. Print simulation, so I should print only the in. Okay, so here's the waveform. Okay, and as you can see, you do have a duty cycle, but if you notice, excuse me, it has this ringing effect where it goes below the negative rail, above and below, and if you notice, it looks like it's dampening. Okay, so let's explore that a little bit more. Let's run it for a longer time. Let's see if it settles out. And it looks like it does. It looks like at the beginning you have the ringing, and then toward the end it settles down. Okay, so you have that. So how do we take care of that problem? This problem where it actually rings and goes below negative rail. Okay, well, one thing that you can do is you can actually put a little damper at the primary. Okay, excuse me. And typically, if your coupling capacitor is 1, you use a 10 times bigger damping cap. Okay, and then what you do is you find the characteristic impedance of the inductance divided by your capacitance. So let's go ahead and do that. Okay. So in this case, let me go back. So, okay, it's a 264. Is the inductance, and the coupling capacitor okay. So let's see what that is. So it's 264 is 6 divided by 1 close. Okay, so it's 16.2. 16.2 ohms. Okay, so what we can do is we set this resistor to 16.2 ohms. So basically this is R damp and C damp. Okay, so let's see if it works. Okay, big improvement. It only rings once and that's it. Okay, so you get that type of waveform. Okay, so now you'll notice one thing, that it's not swinging from 0 to 12. Well, let's see why. If you notice, I have my label here, and it's actually connected to the top of the inductor. Okay. Well, what does that mean? Well, since you have an inductor, it's actually connected to ground. Okay. So there's no way you can go all the way to 12 volts and go to 0, because if you go to 12 volts and 0, the average would be half of that. It would be 6 volts. Okay. But in reality, this is DC ground. So the average voltage at this point should be 0. It should be ground. Okay. So that's what happens, and that the average voltage, because this is a DC point, because it's you have DC connected through the inductor and through the resistor, this has to average to 0 volts. Okay, so that's why the signal, if you take the average of that, it's going to be centered around 0. Okay, so that's a very important concept, and you will see how that affects your output. So basically, by the same token, we should have the same waveform basically at the gate. Okay, and since we're connected through this resistor and to this inductor, you're going to have the same scenario here. Okay, so let's go ahead and see the gate. Okay, and you'll see that it also has another second phenomena. Okay, so here we have the input, and here we have the output. Okay, basically same story, in that now it's centered around the DC volts. Okay, but we also have another little problem, in that we have a little bit of ringing. Okay, how can we get the ringing? Well, the ringing is because remember that we have a coupling coefficient. Hello? Yeah. Okay. Hey, let me talk to your mama. Is she driving? Hey, someone just tried to call in Spanish that we owe 2 months in utility and that they're gonna cut our electricity. Yeah. No, no. It was a scam, Marta. It was a scam. No, because then I said, we don't know anything. And I said, what is your telephone number and what is your name? And she hung up. Uh huh. How the hell are they getting our number? I'm thinking of changing our number. But Jesus. Then that means everybody, no one can get a hold of us then. Okay. But anyway, that's what happened. I'm like, bye. Okay, now the reason that it's ringing is because the leakage inductance, which was composed of 300 nanoseconds, is actually in series with this L7. And since this resistor is low, okay, it's actually ringing with the gate capacitance of the 1 nanofarad. Okay, so basically you you do the same thing. Basically, you calculate what would be the resistance that you need to damp it. In this case, it would be the square root of 0.3 microhenry divided by, in this case, let's go with 1. Well, let's change this to 2 on the schematic just to make it consistent with this. So we need a 12.24 damping resistor to squash or damp the ringing. Let's go ahead and put this to 2 nano. Okay, and this is the series resistance. Let's go ahead and raise it to 12, approximately 12 ohms, and let's see what happens with the ringing. Okay, and you notice the ringing is gone, and if you want, you can use a little bit bigger resistor to get rid of that, but for all intents and purposes, that should be good enough. Okay, so now let's find a solution for this little problem, and that uh, that it's centered around 0. Okay, now let me go ahead and mention another uh, problem with this. Okay, in that if you vary the duty cycle, this actually shifts. Okay, in other words, if you were to reduce the duty cycle to, let's say, 0.1%, then it shifts up, or at least it looks like it shifts up. Let's go with 0.1% or 0.05% so you can see what happens. Okay, so now if you notice, when you have a very low duty cycle, then it's no longer centered around 0. It is centered around 0, but that's because the off time is on for a much longer time than the positive. So the average ends up to be very, very low. Okay, so you do end up with uh, a, a pulse that can actually power your gate, but as soon as your duty cycle increases to 50%, then it'll drop from approximately 6 volts to negative 6 volts. Okay, so we're going to fix that. Okay, so what do? We actually put a capacitor, and we'll go ahead and use a 1 micro. Okay. Okay. And then the second element that we're going to use, we're going to use a diode to clamp this node. In other words, when it goes positive, the diode will be reversed, and it will the gate voltage will be 12 volts, and when it reverses, when this becomes negative and this is positive, then it's going to clamp this node to one diode drop and won't let it go to negative 6. Instead, it'll go to negative 0.7. Okay, so let's see how that works. Okay, so now, as you can see, okay, it's almost at 0 baseline, and that's good. So let's do a simulation just to show that the basic shape of the gate transformer will stay almost consistent. We'll use a duty cycle of 0.5 and then 0.5. So basically we're going from a very low duty cycle to a very high duty cycle. Okay. So this is a low duty cycle. Now this is high duty cycle. Okay. Should be this one. Okay. So here we have it. So regardless whether you have a small duty cycle or a high duty cycle, the top of the gate drive is fairly close to 12 volts. Okay. And the bottom is fairly close to ground. Okay. Now, typically this, you want to be sure that it goes all the way to ground. You can tell that right here it's not really at ground. So what we can do is we can add a third component. We can add a resistor. And we can make this around 2K. Okay. Now you can see that Waveform looks pretty good. It is going below ground. Okay, so this will ensure that when the PWM turns off, that the gate drive going to the transformer, or the gate drive going to the transistor, actually does turn off. Okay, so basically this would be your gate transformer. Okay, so let's go ahead and I'll save that, and then here is our two switch. Now what I did is I substituted two MOSFETs. I'm using the IRF 750, and here's my primary, secondary, okay, and I have my forward and my catch, okay. Here's my PWM. I'll go ahead and press run, and this may take a while, so I'll go ahead and edit it so you can see the simulation or the results. The simulation is complete, and we look at the output, and here's the output. We can see the output here. It's 3.27, and we can see that the red, that would be the bottom driver. Let's go ahead and move this to another plot. We'll do a cut and paste. There you go. So this is the low side driver, going from 0 to approximately 12, and the high side as well as driving the gate from 0 to 12. And what's interesting is, if you zoom in, they basically turn on at the same time. And this should turn off at approximately the same time, which is good. If we can get there, there it is. Okay, so they turn off at the same time. So this is a pretty good way of powering your two switch forward. Basically, if you have you only need a couple of passive components and a transformer, this is a good way to implement it, just in case you don't have a high-low CMOS driver. You can implement it with discrete components. Hopefully you will find this useful. If you have any comments or questions, please email them to rbola, which is RBOLA 35618 at AOL.com, and you can email me there. And if you have requests, you can also send a request for the SPICE files, so you can simulate these at home. Thank you for watching.